Let me start my presentation. And hello everyone, my name is Shotaro Kikuchihara. I know my name is a little bit wrong to pronounce, and the true pronunciation is Shotaro. And I am a PhD student at the University of Tokyo. And today I will talk about the extended Lyman-alpha halos around higher redshift Lyman-alpha emitters investigated by the technique what's called intensity mapping. Okay, now let me start with the introduction. Okay, this figure shows the schematic view of the circumgalactic medium and the intergalactic medium around galaxies. And you know, Lyman-alpha halos are created by the scattered Lyman-alpha photons inside the circumgalactic mediums. And the Lyman-alpha halos are found ubiquitously around star-forming galaxies and more extended than UV continuum. For example, in Shotaro et al. 2011, they observed the redshift 2.65 Lyman bright galaxies, and they find the Lyman-alpha emissions are more extended than UV continuum, as illustrated with this figure, or shown in this radial profile. Lyman-alpha emitters here and UV continuum in this here. And Matsuda et al. 2012, they observed redshift 3 Lyman-alpha emitters. This shows the snapshots. And they derive the surface brightness radial profile, and they go down. They go down to the 10 to the minus 20th order of the surface brightness. So here's the question: and the how largely extended are the Lyman-alpha halos? And also the origin or the evolution of the halos are still yet to be understood enough. So we want to answer these questions, but here's one technical difficulties of the detection limit. So in order to resolve these difficulties in our analysis, we focus on two things. The first one is what's called intensity mapping technique. I remember this topic is already touched in the yesterday's talks. For example, in Croft et al. 2018, they took cross-correlation between the position of the ratio of 2 to 3 quasars and the Lyman-alpha emissions traced by the fiber spectra. And what's good about taking cross-correlation is thanks to this, they successfully removed the systematics from foreground and background sources. And finally, they reached down surface brightness down to the 10 to the minus first order. So in our analysis, we also use this analysis. And the second thing, we make advantage of the deep and wide images of the Subaru Hyper Suprime-Cam. And in our analysis, we utilize the data from two large surveys. One is the cosmic hydrogen reionization unveiled with Subaru Chorus. And the second one is the Hyper Suprime-Cam Subaru Strategic Program, HSG-SSB. And here there are 4 narrow bands we use and 5 broad bands, and whose throughputs are represented with these curves. And there are 4 narrow bands, and each trace the ratio 2.2, 3.3, 5.7, and 6.6 Lyman-alpha emitters respectively. And in our analysis, we first begin with the analysis on the UD cosmos field, which is as wide as 2 degrees squares wide, corresponding to more than 10 times the size of the full moon. Okay, and the next, we use the Lyman-alpha selection, but we utilize Lyman-alpha catalog, which is constructed by the Ono in prep. So here I briefly shows what they will do and what they done here. They first detect the sources with using sex structure, and next they carried out the machine learning and visual inspection onto the detected sources. They use the convolution neural network, and they classify real Lyman-alpha emitters and remove the spurious sources, and they finally constructed the final catalog. These two figures shows the snapshots and the positional distributions of the selected Lyman-alpha emitters. And the number of the finally selected Lyman-alpha emitters are listed here, in total as many as the 2,000 Lyman-alpha emitters. Okay, next, let me explain more detail what the intensity mapping is. Our goal is to derive the Lyman-alpha surface brightness, which is schematic is here. So first we took the cross correlation between the position of the Lime alpha emitters and the Lime alpha intensity, which is traced by the narrowband images. In this calculation, we took the mean of the pixel value inside the annuli at distant r from the central Lime alpha emitters. However, taking this cross correlation is not enough because this result includes not only Lime alpha emission, but also the PSF and the sky background. So we have to subtract the contributions from this PSF and sky as a systematics. So in order to evaluate that, we took cross correlation between the position of the foreground sources and the Lime alpha intensity. And this result yield the surface brightness from these two contributors. And we select the foreground sources so that the magnitude and the FWHM distributions are matched to that of the Lime alpha emitters. And subtracting these systematics from the total surface brightness, we finally derive the Lime alpha surface brightness like here. Okay, so now we adapt this analysis to our samples and finally obtaining these results. These results shows the surface brightness profile versus the radius at the redshift 2.2, 3.3, 5.7, and 6.6. And you can see at these four redshifts, our data points reach to the order of the 100 physical kiloparsec size. And in order to test our results are valid, we compare our result to the previous work. This figure compares our result at the redshift 5.7 to the previous results from the Leclerc et al. 2017, who detect the Lime alpha emitters at the Hubble ultra deep fields with VRT mutes. And in order to do a fair comparison, we constructed the subsample whose Lime alpha luminosity is at this range to match the Lime alpha luminosity of this object. And you can see that our profiles are smoothly connected to the this profile around these regions. So to sum up our results, we find the Lime alpha halos extended up to the order of the 100 physical kiloparsecs at this redshift, and outer profiles here are consistent with the extrapolation from the inner profiles if we match the Lime alpha luminosity. Okay, now let me go to the discussion part. First, let's look at the evolution of the halo profiles. This figure compares the profiles at these three redshifts, and the field symbols shows our results, and the open symbols shows the Leclerc et al.'s results from the Muse Hubble ultra deep field. And to do fair comparison, all of these samples are constructed so that the Lime alpha luminosity are in this range. And you can please look around here, and you cannot see a significant evolution from redshift 6.6 to 3.3. However, next, please look at this figure. This figure shows the same as the left one, but corrected for the cosmological dimming effect with this order to match the redshift 5.7. And we plotted our result at the redshift 3.3 to 5.7. And here you can see that there is a possible decreasing trend from redshifts at redshift 6 to 3. And the next discussion is a comparison to the simulation at the reionization epoch. In this figure, we plot our result at the redshift 5.7 here, and we compare to the simulation result of the Zheng et al. 2011, who carried out the Lime alpha radiative transfer and the hydrodynamic cosmological simulation at the similar redshift. And this dashed line shows the contributions from the resonant scattering in the circumgalactic medium, which is illustrated like this. And this dotted line shows the contributions from the satellite galaxies, which are around the central galaxies, the Lime alpha emitters. And this solid black curve shows the sum of these two. And you can see our result prefers the scenario A, the resonant scattering. And we did the same test for the brighter subsamples, whose luminosity is in this region. But even in this case, our observational results underestimated the model, so the conclusion. Okay, now this is a summary. We select the 2000 Lama emitters at this redshift using Subaru HSC images and machine learning technique. We detect the line of halos with intensity mapping technique, and finding the halos are extended up to the 100 physical kiloparsecs at high redshift. And we find the possible decreasing trend of the profiles if we corrected for a cosmological dimming effect. And finally, we compare our results to the simulation that's redshift 6, and our observational results agree with the resonant scattering in the circumgalactic medium. In the future, we will investigate the origin of the halos in more detail with intensity mapping or other lines such as Balmer alpha or O3. Okay, this is the end of my talk. Thank you very much.
Thank you very much, Shotaro. Are there questions? So while people ask questions, I have one. People write questions, sorry, I have one. One of the things is you're basically selecting your sample based on Lyman alpha luminosity. And are you worried that the sample might be biased? And wouldn't it be easier, not easier, but wouldn't it be better to basically do cuts based on, say, stellar masses or something similar?
Your question is about when constructing this kind of subsamples?
Yeah, so your subsample is limited by luminosity on Lyman alpha. And right. I'm worried that at redshift 6, you are sampling a very different population than at redshift 2 while doing this cut.
But when I compared to the low redshift, we matched the Lyman alpha luminosity. So I think in this case we did a comparison. But are you worried about the difference of the halo mass or something between the low redshift?
I wonder if cutting by stellar mass would be a better and more physical way to compare the two samples.
I think that's another way, and that's the thing we haven't done yet. But yeah, I think that's the next thing we have to investigate.
Okay, so there is another question by Matt. Nice results. You prefer resonant scattering instead of local satellites, but how would your profile look in the case of halo gas that is fluorescing because of the ultraviolet background?
Is that question is about the recognizing between the fluorescent scenario?
Yeah, so how would fluorescent scenario make this plot different?
I think the with the current data set, I'm not sure a fluorescent scenario how largely the fluorescent scenario affects this result. I think comparing with the other lines are also necessary to discuss about that. But I think that's the important point to discuss when about the origin. So now please let me discuss at the Slack channel.
Okay. So another question is, have you estimated the incidence of AGN in the 2000 redshift 2 to 7 LAE sample?
We haven't yet checked how many AGNs in our samples, but yes, the making the cross matching to X-ray catalog or something, and investing in similar things, will be important. Yes. But currently no. That's the next step. Yeah.